Good afternoon. 안녕하세요. My name is Matt Brandwein. I lead the product group for machine learning at Cloudera. So my team is responsible for all of the software that sits on top of the Cloudera platform to enable data science and machine learning at scale. Today, I'd like to add a little more detail to the overview you heard this morning from Mick Hollison and Amara Wadala about what it takes to deliver data science at scale in the enterprise, to share some of the business and technical challenges that we have seen working with our customers. Before I begin, I wanted to ask, how many data scientists are in the room? Raise your hand. If one data scientist, two. How many people support data scientists, represent an IT function or a shared services group that have to enable data scientists? A few. So this presentation is for both groups. How do we bring together the data scientists and the data platform teams? Before we begin, I want to revisit the context for what we're trying to do. There are many opportunities for machine learning and artificial intelligence in a variety of industries. This is not the question. There's never just one problem that we're trying to solve with machine learning. It's never just one model. The real question is, how do we create an environment where you can deploy many machine learning capabilities, where you can create the artificial intelligence factory that Amr talked about, where you can invest multiple times and each investment builds on the next? How do you make it easy and repeatable to go from the lab to production over and over again? It's important to keep in mind that the start of this journey is data. You cannot do data science without good data management. And once you have that foundation in place, then we can start to talk about the more interesting applications of data. I also wanted to share some perspective on why now is the perfect time to invest in machine learning. There are three trends that make it now possible for machine learning to become pervasive. Because many machine learning techniques are not new. They've been available for decades, but only now, in many cases, do we have enough data for training these models, where you can put a sensor in your machinery, you can collect data from a mobile phone, you can put trackers in your web applications, you can observe streams. We now have enough data. Secondly, there is now enough computing power to train some of these models that would have been impossible to train in reasonable time just a decade ago. I remember when I was in university, a lot of the algorithms we learned were simply academic. There was no chance we'd be able to do them in practice because we didn't have enough computing power. But now with widely available CPUs and GPUs and in the cloud to get these resources on demand, we now have supercomputers at our fingertips for just a little bit of money. And then lastly, the algorithmic landscape has changed. It used to be that the only way to adopt machine learning in the enterprise was to buy proprietary software from companies like SAS and only have a few people be able to use them. But now, there is incredible innovation in open source where anybody can download off the internet the latest implementation of a particular technique and then bring it into the enterprise using popular open source languages like Python or R, and it's now democratizing access to complex data science techniques. Also, this makes this much more affordable because anybody can have access to these advanced capabilities. What becomes interesting is that your advantage, your competitive advantage, becomes not the algorithm, because the algorithms are commodity. Your advantage becomes the combination of commodity algorithms with your data, if only you can have access to the algorithms and the compute with your data. Now, these three trends have also made some new things possible. At Cloudera, we keep track of what we call emerging capabilities in machine learning. These are techniques that are only just now becoming possible. These may be old techniques, again, for which we did not have the data, the computing power. And in some cases, these are new techniques. In some cases, the economics have changed, where these are now affordable, where instead of you needing to decide that you would invest 6 months in an implementation, now you can do these things in a few hours. To give you a few examples of the kinds of research that we do at Cloudera, I want to highlight 2 of these reports specifically. I should mention what these are before I go on. Cloudera has a team of applied research engineers called Fast Forward Labs. They read hundreds of academic papers and choose the most interesting techniques to bring them from the lab into the enterprise and make them practical for you. And each of these reports includes a description of the technique, the latest capabilities, different implementation options. There's a working prototype. To give you a few examples, our most recent research report was into a technique called multitask learning. Multitask learning changes the way we think about machine learning. Traditional machine learning learns how to do one task at a time. We fit a line to a data set. We learn how to predict one outcome based on one training set. This is not how humans learn. Humans learn many things together. Understanding one language makes it easier for me to learn another language. Multitask learning concerns the ability to learn multiple models at the same time and to predict multiple outcomes at the same time. The second technique that I want to highlight, just as an example, is interpretability. This has never been more important as machine learning becomes pervasive, to show why a model is behaving the way it is. It's perfectly fine to highlight that I'm approved for a loan or that my email is spam. But what I really need to understand is why it made that prediction and what I can do about it. Furthermore, for compliance, especially in Europe these days, I need to demonstrate why the black box model did what it did. To give you a specific example, this is a prototype we built for the telecommunications industry, where on the right hand, or on the left, forgive me, you have a customer and their probability of churn to another provider. And that's interesting, but you can't do anything. You cannot take action with that. You need to understand why they're going to churn and what you can do about it. And so we highlight here the primary contributing factors so that if you can change them from a month-to-month contract to an annual contract, their probability of churning decreases substantially. I just highlight this to show that there are new capabilities you can bring to your data, but this is just the beginning. This alone is not enough. The challenge that our customers find again and again is that there is the generic version of churn reduction, and then there is your specific problem with your specific data set for your specific company. And the difference between those we call the data product gap, which means there is no commodity software that can solve your machine learning problem. What you need is the ability to adapt these techniques to your business situation so that you can own the capability and you can own the outcome. If every one of you can acquire the same commodity capability, there's no difference between your companies. Your innovation depends on your ability to incorporate this into your specific business. The way that innovative companies do this is they build platforms for enabling data science at scale. If you look in the data center of Uber, Facebook, Airbnb, innovative Silicon Valley companies, they each have a platform that looks like this, where they have the ability to develop and share insight, the ability to train on hyperscale computing, and the ability to deploy and manage complex models at scale. And in the enterprise, we also see the requirement to be able to manage these kinds of capabilities on multiple infrastructures, ranging from on-premises to private cloud to public cloud, because our customers are changing how they invest in infrastructure. So what I want to spend the rest of the time today sharing are some lessons learned about why building that for the enterprise is so difficult and some of the solutions we have developed to help. The first challenge is about access. Access to data, access to environments, access to resources, and the ability to share. Data scientists experiment for a living. Their job is to try many things out, to fail often, to iterate. They're building a portfolio of investments. To do that, they need access to all of your data. They need access to not just a little bit, but all of the data that you can store, because they don't know what is relevant when they start. They needed to explore. Secondly, they need access to use the tools they need to do their job. This is more complex than business intelligence, because for business intelligence, all we need is SQL, structured query language, right? Tableau just needs to talk to a database. Data scientists have a much more diverse set of tools. These tools are open source. These tools change. Every month, there is a new tool, a new library, a new technique. And if you try to restrict what tools data scientists can use, they will not use the tools you give them. They will extract data from your platform, they will move it to their laptop, and you will never see it again. And this will create silos, this will create security issues. All of the challenges of scale are compounded by this diversity. Data scientists also need more interesting compute than BI. They need 1,000 CPUs for 2 hours. I might need 40 GPUs for an hour. These needs are elastic. They change. They're unpredictable. And one data scientist could consume your entire distributed computing environment easily. And then if you have 100 users, and they are each working on different projects and different timescales, this becomes very difficult. And then lastly, all of this diversity needs to be managed if you're going to enable these data scientists to share with one another, so that the work that I do can be shared with each of you, for example. All of these needs for agility and flexibility directly conflict with what traditional IT and data management is required to support. Data scientists ask for a new version of Python on the Hadoop cluster. IT says no. Data scientists want to install R on a gateway node. IT says no. What happens? The data scientists leave, and you have no innovation. To enable data scientists to come to the data platform, we had to invent a new product to support this. You have to give data scientists a familiar experience that looks exactly like their laptop, that supports the languages, the libraries, the compute that they need. but works within the security and management constraints of the enterprise. We call this product Data Science Workbench, and I want to give you a brief demo of this product so you get a sense for what it really does. And you'll forgive me, I'm not brave enough to do a live demo, so I'm going to just walk you through a few screenshots of the product, and we can maybe do a demo later at the booth. So this is the home screen. When you log into Data Science Workbench as a user, this is what you see. It is all web-based. There is nothing to download. You can run this on any web browser, so there's no data security leaking, nothing to be left on your laptop if you leave it in a taxi. Data scientists work on projects. So the main list is of the projects I might be working on. We also support multiple teams. So if there are many data science teams spread out through the business, as is a best practice, to have some central data science capabilities, but also data scientists in the line of business. We support that as well in a shared multi-tenant environment. When data scientists log in, they're automatically authenticated to the secure Hadoop environment. So if you are a data scientist and you ever had to figure out how do I authenticate to a Kerberos-enabled CDH cluster, that is incredibly difficult and incredibly frustrating. And we make it easy because you just log in once and you are now in. Inside a project, it's exactly like you would see on a folder in your laptop or in your Git or GitHub repository, because most data scientists use version control. What I'm going to do now is show you the interactive experience, because it's nice to see the code, but you really want to do is run the code. So I'm going to click on this Workbench button here, and it's going to take me into the interactive mode. Again, this is all still in the web browser. I've got a development environment here where I can write the code, syntax highlighting, autocomplete, it's all there. But what I'm really doing next is selecting my compute environment, where I can pick the language and I can pick the compute that I want. And it's now going to provision for me an interactive environment where I can write and run code at scale. If I had GPUs on this machine, they would be available as well. And you can't see because it's hidden by this terminal here, which I'll describe in 1 minute. When you run this code, you get a rich visual output like you would see in a Jupyter notebook, if you're familiar. And the idea is that you want your code to remain code. This is what you version control. This is what you deploy to production. This is just for sharing. And that balance between code and output is very attractive to data scientists thinking about deployment. Of course, if you couldn't customize the environment, data scientists would leave the environment. So we give you a full web-based terminal. This is all still virtual, to install custom packages, to integrate with any third-party tools you might want. Anything a developer can do at a terminal or in a Jupyter notebook, they can do in Data Science Workbench. The way we enable this is with a modern architecture. Cloudera is using container technology very heavily to empower this capability. When you create a session, we are creating a pod of containers that give you fully isolated data science environments. So you can have whatever you want, with whatever resources you want, as many concurrent users as you have resources in this distributed environment. And you can scale this up and you can scale it down. You can run it in the cloud, anywhere you have Kubernetes. We actually give you Kubernetes to make this even easier if you need it. And all of this has direct access to the Cloudera environment, so you can push down distributed computing to the cluster as well and access all of the data. And because it's based on the Cloudera environment, all security, all governance, all auditing is respected. and IT can centrally manage it using Cloudera Manager. So it's the easiest way to add self-service programming to your Cloudera environment. The second challenge, now that we've solved access, is about reproducibility. Data scientists are researchers. This means that when they run an experiment, they want to reproduce it if I revisit a week later or I share it with my colleague. This is very, very difficult. If you think about the number of variables that can change between experiments, different data, different feature inputs to a model, different libraries, different algorithms, different parameters, every change means that you can't reproduce your experiment. And I've seen many data scientists' laptops, and they have files in folders with names like experiment1.final.final.final. It's insane. What you need is the ability to version all of these parameters together so that the entire experiment can be reproduced. We recently introduced a new capability for managing experiments, where every time you kick off a batch experiment, we take your entire environment, we package it in a container, and then we version control the container with metadata about how the experiment ran and the resulting model. And so you can move forward and backward in time, you can compare the results, you can extract the model from each experimental run. So just to give you an idea, here we are in the Workbench again. I've added some code to log the metrics that we care about. This could be anything. We can log anything you like. It's just key value pairs. And then you can also save model artifacts. Like here is a model that we've trained, and we're just going to save it here. When I run this as an experiment, instead of an interactive session, I can also specify input arguments to run through different parameters or hyperparameters. Instead of just running, it's now going to kick off a build process. And this is my experiment tracker, where I can see all of the variables between all the experiments. But when I kick off an experiment, it's actually going to be building this container for me automatically. I don't need to think about containers. I don't need to be aware of what's happening. But just so you know, once the container is built, we execute the code inside the container with a fully separate version of all of the dependencies for Python and R. And when the experiment is done, we have the metrics, we have the model, it's saved to my list, and now if I want, I can take that model and I can re-import it to the project to deploy it, which is the next problem we solve. Once I've got a model, how do I get it to production? There are many ways to think about production. To some data science teams, production is a report that I deploy repeatedly. To some data scientists, production is a batch data pipeline that I run every night, every hour. To some data scientists, production is a stream, and I'm doing real-time scoring. To some data scientists, production is a database that is doing real-time processing as records are scanned or served. However, these days, the most popular request we see is for microservices, for models to be exposed as web services, REST endpoints. This is very, very important and very, very difficult. Usually, when a model is developed, it gets handed off to a data engineering team or a software engineering team who work with completely different tools than the data scientists. So data scientists write their code in Python and R, and the software engineers develop in Java or C or anything else. And the model has to be rewritten. It has to be translated. You lose information. You can't guarantee it's the same model. If the data scientists try to put the model into production themselves, as some customers want, they have to learn new skills. Data scientists are not software engineers. They write code, but they are not software engineers. To require them to understand containers and Kubernetes and web services and debugging, it's too much. If a data scientist is already a unicorn, you're now requiring the unicorn to learn new tricks, and it's too complicated. What we want is to give data scientists the ability to take the models they've built in the languages they know and deploy them directly to where they can impact the business. So we also recently introduced a capability to, with one click, deploy any code as a microservice. It's very simple. You have a function, you have a file which contains your scoring code. There's a function that is the scoring logic. Here it is. We're importing a scikit-learn model, and then we're doing predictions. You say how much compute you want that model to have, and you're done. What does this actually look like? Now, by the way, I should mention, the nice thing about this is because it's attached to your Cloudera environment, if you need to do lookups. So let's say you have a propensity to buy model that's based on your customer ID. That model has more feature inputs than just the customer ID. It needs to do lookups from a database. If you're building this on Cloudera, you have the data right there. And so your API can be very simple, and the lookups and the scoring can be very complex. Keep that in mind. So here's our project again. Here's the trained model from our experiment that we just ran. Here's the scoring function that I've written. I'm going to deploy a new model where all I have to specify is the name of that file, the name of our function. I can provide some basic documentation if I like. If I scroll down, I again pick the environment and the compute profile, the number of replicas, because this can be automatically load balanced, and I say, go. We follow the same process. We build a new container that contains the code, the environment, the dependencies, all the security configurations, everything you need. And we insert a web server, just a lightweight web server that takes an HTTP input, it tunnels it into the function. It's still Python or R, nothing has changed. And it takes whatever that output is and serializes it or deserializes it back as HTTP output, all automatically. So when it's building a Docker image. When it's built, it then gets deployed to the exact same Kubernetes cluster where you built the model. And now it's deployed, and that's it. And this takes a matter of minutes. And now I have one or more containerized microservices running, serving my model code. I haven't had to talk to IT. I have not had to talk to a data engineering team. We're just finished. And I can call this model using our web endpoint. You can provide an access key, so there's some security. We include a basic tester as well, so you can test your model. There's some simple debugging to start. This is our first iteration of this product, but you can at least see all the replicas and how they're performing. And now I've got my deployed model, and I can just observe it. So to summarize, we talked about 3 challenges. We talked about access to data for analyzing, reporting, and sharing. We talked about scaling, training, and reproducing results. We talked about deploying to production. The full data science lifecycle in one environment, the data scientists can access and bring their favorite tools. There are many benefits to this kind of architecture. It's really about empowering your team to move faster, to adopt new techniques, whether it's the research that we talk about or whatever your team is interested in. We can help you prioritize data science projects, deploy them on your data faster with this kind of capability. It makes it easier for data scientists to have a business impact because they can expose their work in ways that can be consumed by software teams. And if you are on the IT team, this is something that is very easy to give your data scientists so they don't leave the environment, upload the data to some other provider. You can leave everything where it is and just bring the data scientist to the data. So that's great, but I also want to give you a look at the future. So because you were nice enough to spend your time with us here today, I want to give you a privileged view of what we are investing in next, because this is just the start. There are a few problems to solve next. As our customers increasingly find that data science requires lots of compute, they often don't have room in the data center to deploy, and so they look to the cloud. And they're not moving their data to the cloud necessarily. They're often using the cloud for new data, unstructured data, data that originates in the cloud, and they just need a compute environment there. Or maybe they do have the data on premises, and they want to move it to the cloud, run a bunch of model training, and then take the resulting model back down and only pay for what they used. This requires a common experience that is native to the cloud that can be deployed anywhere seamlessly. The investments Cloudera has made in container technology will enable this transition, where we have one set of products, fully containerized, that can be deployed anywhere. Furthermore, as a data scientist, you don't want to think about clusters. You don't want to think about how many nodes or how much memory. You just want to run your model, and you feel like your laptop gets really big when it needs to. So we are designing systems that, given an auto-scaling policy and enough infrastructure in the public or private cloud that you provide access to, we will automatically grow and shrink our compute environments with CPUs or GPUs to support the needs of data scientists. This is another aspect of what cloud native means. Another aspect of cloud native is seamless dependency management. If any of you have tried data science at scale, it's not enough just to point your code at a machine. You also have to get all of the libraries and packages and Python environments to that machine. If you now have 100 machines or 1,000 machines, that's a lot of coordination. And then if there are 1,000 users that each have their own environments and their own dependencies, that is very, very complicated. So, using containers, we can ensure that every user's environment is automatically distributed throughout multiple clouds, automatically at scale. The last investment area is what we can call model operations. So once you've deployed a model, you are not finished. You never deploy a model once. You deploy a model as many times as you need to keep the model accurate and risk-free. And this means you need to monitor the performance of the model. Is it drifting? Is the model still accurate? Is it time to retrain the model? Do I need to take the model offline? Do I need to deploy multiple models and experiment to see which one is getting the better result? All of these model lifecycle activities need to be built on top of this foundation. We also are looking at ways to deploy models outside of Cloudera, to take these containers and run them in other clouds, to run them at the edge for IoT applications, and to monitor them remotely so that you can re-trigger and retrain. We are actually working on new research into a technique called federated learning, which concerns the ability to have models running at the edge, retrained at the edge, and then redistributed throughout an IoT network. This will be enabled by these new model operations capabilities. In the future, the architecture looks different than what it does today. Today, if you recall, you have your Cloudera environment, and then you have this containerized data science environment next to it. In the future, we see the entire Cloudera machine learning environment running in containers, where you have data science, data engineering, and models all running on a common containerized platform, running in your choice of Kubernetes environment, in Amazon, Azure, Google, Red Hat OpenShift, Pivotal, whatever you need. Same product running anywhere. With shared services like workspaces, your project environment, a feature and model catalog for sharing models and building transferable learning, all with access to the shared metadata, schema, security, governance, access to your existing Cloudera clusters and environment, if you still want to push down compute there, and access to native object storage. So one platform for end-to-end machine learning that can run anywhere with access to shared data and your existing environments. We're very excited about what we think we can bring to our customers to give you the ability to build your own AI factories, just like the large tech companies have already done. We can bring this, hopefully, to you. But this is also just the beginning of a transition for Cloudera. As you heard about this morning, this is one of the top 2 investment areas for the company to make data warehousing more robust and to make machine learning the future of your enterprise so that you can build on your foundation to get to AI. That's everything I had for today. I hope this was a helpful view into some challenges you're likely to see and some of the things we're doing to help address it. Thank you very much for your time.